So thank you. It's an honor to be here. I think the last time I came, Patrick was a graduate student, so it tells you how long it's been. But my sister also graduated from UVA from the law school, so I've been here before, and it's definitely a good thing to come back and to see some people that I haven't seen in a while and to interact. And so it's my honor to talk to you about some of the work that my group has been doing. Actually, even for this trip, I was so excited. I brought a couple of my own graduate students, and so they're here to work with Patrick in his lab. And so they have to take time out, I guess, to come and hear me talk again. But thank you also for coming over. So what I'm going to do is talk today about some of the things that we're doing for packaging and the advancements of some electronic devices. And before I get into that, I was also thinking about the concept of what some of the grand challenges are. And one of the things I want to point out is something in education that we're seeing as well in my time at Georgia Tech. And so I don't want to go over a big deal in terms of our department, but the main thing I want to point out is that we have a very, very large mechanical engineering program. And so these are the number of degrees that we granted in the 2017 school year. So you can see we're producing a lot of students. We have right around 3,000 students in our department, large number of faculty. And so there's good things about that. There's also some challenges. And so one of the things that we say is that our size allows us to do a lot of different things, but our size also gives us the opportunity to kind of innovate with the number of students that we have. And so how do you bring education to this number of students rather than like I have a laboratory class that may have 300 students, you're just kind of pushing them through. What are some neat things that you can do? And so we call this aspect the education to innovation continuum. And so this is something that some of you here have probably heard of, our invention studio, but I'll kind of talk about what we're doing. We've created these spaces for our students to do innovation work, to really learn outside of the classroom. So there's a lot of things that we teach in the class, but what we want to do is sort of give back resources and time and just say, take what you've learned and just go do whatever it is you want to do. And so we have what's called the Montgomery Machining Mall, which is a world-class machining facility. We have the Invention Studio, which is our maker space. Actually, I have to be back in Atlanta tomorrow morning for the dedication of our new space. We have this reconfigurable space here where students do design projects. All of this is contiguous on one floor. We have another space here which we have our student competition center. And then we've added on top of that something called the Inventor Prize, where students can take these kinds of projects and they can compete for, let's say, money and help with startups. And so you can tell that this is kind of nicely lit. This is actually put on television, Georgia Public Broadcasting. So we have students that are doing very, very interesting competitions. And then we have other things that we do. We take this program called CreateX, which has started, that actually trains students on creating their own startups. And so what we find is that even though you may go through this process, you may not necessarily want to start your company, but we do find companies wanting students that are willing to take risk. And so by interjecting that back into the educational process, we find that it helps to excite the students. And so just to show you some examples here out of that student design competition, we have taken like this group of students, they've actually converted a Chevy Camaro into a hybrid. And so they competed on the national scale. And so you can see basically they did quite well. And so what I always tell my faculty when they complain about this, what's the class that they take to learn how to do this? And so the thing that we're trying to do is interject back in, how do you give students credit for this? Calm the faculty down. There's not necessarily you have to take this class, learn how to do everything about a hybrid car and then go build one, but we can teach students on the fly through hands-on. Here's another one, an example of another ME student. Went through that process. He was working in the Student Competition Center, learning how to convert cars, make electric vehicles. He went through the startup process, and so now he has his own company where he could take your car and convert it into an electric vehicle. And so that's a startup in Atlanta. Again, where do you teach this in the classroom? And so we're coming around realizing that when we give our students these resources, that there's amazing things that they can do that as professors, we probably put limits on them. And so they're doing these things outside. The very last one, another one, a group of ME students, they came up with this company called Firehud. This is another one where they make a heads-up display inside of a firefighter's mask. They have a forward-looking infrared camera, so wherever the firefighter is looking, it displays the temperature of whatever they're looking at, also displays their biometric data. It sends all that information back out to the fire captain, and the fire captain can basically take control of the temperature inside of the building as well as the status of all the firefighters that are in the building. So again, this is a very interesting concept. Again, I always tell the faculty, what class do you take to learn this? And these are undergrads. And so again, this is something that I say that in terms of how do we train students with the movement of the makerspaces, we have to figure out in academia, how do we take the governor off and let students be innovative while still keeping the basics and the fundamentals in the educational process. And so I think this is a concept that we really have to think about in rethinking the way we do education in mechanical engineering. So I'll get off my soapbox, but hopefully you kind of get this in terms of what I'm trying to say in terms of how we push this forward. So now I want to move on to the topic of the electronics. And so I think when I show this picture, most of you are aware of what everything is here. We have OLED televisions now. I've worked in that space with some of the packaging for OLEDs and organic electronics. You see a number of different devices here that may utilize these, tablets and phones, wearable devices, electronics that are going into cars. So now there's the electrification of cars. 40% of the cost of a car now, of the average car, is actually going into the electronic side. And then there's more and more being pushed into outer space in terms of electronics as you create CubeSats and these low Earth energy orbit satellite constellations that are being designed. And so these are sort of the standard things that we've been working on for a number of years. So what's sort of the future here? Well, there's a lot that's being done here, but part of the future is going to be flexible. And so when you look at this is, I'll actually show you a video of this particular screen. That's actually a flexible high definition display. Actually a touch screen display, and you see flexible lighting, you see now skin sensors, so these are coming along. Here's actually a video of this display, and so we've worked on some of the coatings with applied materials that went into this. And so here's the interesting thing about this is that, so this is, you can see how it's folded, touch screen. I took this video in 2015. So these are things that have been on the drawing board for a while, but the concept here is that we're starting to push this forward into technologies, and we're trying to see where it goes. And I'm going to explain to you some of the problems that you have in terms of trying to make this kind of technology. We also have, this is another faculty member at our university, Hong Yao. He makes a lot of these skin sensors. He came from the group of John Rogers. And again, when you look at this, the reason why I'm showing you this set of slides or in this video is because this gets back to the concept of human-computer interaction. And so these sensors are here on his arm, and he's actually using that to control the drone just by movement. And so now we have the opportunity to take sensors, put them on the human body, and actually have nice interfaces with machines. And so we're going to push this even further. I won't show the whole video. You have neural implants. You also have, this is another one by Hong, where he actually makes a mouth device that you put in your mouth and actually measures sodium intake while you're eating. Again, these are these flexible sensors that can actually be implanted or worn on the body. And part of what we're trying to do is figure out how do we keep pushing this technology. As you see before, everything that I showed you in that first slide of electronics is rigid. Now we have flexible. And so that means that there's mechanics. That means that the typical things that we did before with heat transfer doesn't necessarily work in this environment, and so you have to address these as you push this forward. The last thing I want to mention here before I get into some of the aspects of where we made some contributions is that there's this whole concept here in the future of sensing the person. And so when you look at this, one of my mentors, I'm very fortunate, is Ken Washington. He's now the CTO of Ford. And he was telling me, he says, in the future, I want you to be able to walk up to your car and your car just recognize you. You don't have to have a key. You don't have to talk to it, but it recognizes you and it understands you. And so part of that's going to go back to how do we sense the individual rather than only us putting input into the devices, but how do we understand the signals and the biometric data off of an individual. And so here you can see, this is actually an Under Armour shirt. So in the NFL Combine, these shirts that are worn by the athletes have sensors in them. And so they're recording all kinds of things when they're going through the NFL Combine. Ohio State University uses some of this technology to look at their players. This is a sweat sensor made by Josh Hagan at the Air Force Research Lab. It's very similar to this kind of sensor. I believe this was inspired by work out of John Rogers' lab. It is a hydration sensor. So it tells you if you're dehydrated or not. So, and again, you can just see all of these kinds of things. We're going to keep pushing these forward. But there's another part to it. I like this little Dilbert cartoon. And basically, I'll give you a chance to read it, but basically it's saying that, hey, we're giving you this watch to wear, and Dilbert saying, hey, I didn't know you cared so much. And at the end, you can see right here, employee 479 doesn't have shallow breathing. You can give that person basically some more work. And so we have to worry about the ethics of what we do with this information. I think there's a lot of concern over that, but I think these are challenges that we can address in the future. So one of the areas that we've worked on is the packaging of these kinds of devices. And so when you look at this, we've worked on what are called barrier films. And this goes back to the original work with the OLEDs and some of our work with solar cells. And the main thing is that you don't want to expose these devices to the outside atmosphere. They need to be flexible, which means that the coatings that you put on top to prevent the exposure has to be very thin. And so here you're looking at this concept here of water vapor transmission rate. Typically water is the bad culprit. And you can see that if you look at your typical food packaging, it has a water vapor transmission rate on the order of 1 gram per meter squared per day. What we're looking at when we get to our devices is something down here on the order of 10 to the minus 6 grams per meter squared per day. That probably means nothing to you, but I thought this was very interesting. One of my friends at NREL calculated, she said that if you were to wait 20 years at a transmission rate of 1 times 10 to the minus 6 grams per meter squared per day, after 20 years, you would have 7.3 microliters of water that has come through that film, which is, if on a 1 meter by 1 meter sheet, that would be a 20 nanometer thick layer of water. And so you have these very, very low diffusion rates. And so first of all, how do you measure that? You know, graduate student time is not that cheap, or that people can't be that patient. But the other thing is, once you've developed these highly dense coatings, how do you make sure that they're mechanically reliable? And so that's what we've gotten into in some of our work. And so it's all about defects. And so when I deposit my films, I have to make sure that I don't have these defective pathways. I need to have high density. And so we're looking for these defects that are inherent to the film. You're looking at defects that occur because there are defects on the substrate that you're depositing the film on. And here's the issue, is that a water vapor molecule is only 0.3 nanometers in diameter. So you have to have very, very tight control over what you're depositing in order to have inherent, very, very low diffusion pathways through this particular material. And so that's sort of what we've been working on, is trying to understand defects in these films. And what I'm going to do is talk a little bit more about the macro scale effects, because a lot of times these films are inorganic layers. And so you can think of just glass. So you can imagine I can put down a layer of glass. I'm not going to get this kind of water through there. But now think back to flexibility. How flexible is glass? I need to make that very, very thin. What are the limits? So when I look at this, I may have any kind of deposition process. So we've interacted with 3M, we've interacted with the whole center in the Netherlands, and we've also made our own, these multi-layers, and they actually go on these polymer substrates, or you could deposit directly on top of the device like they would with, say, an OLED display. And so these are all kind of interesting ways that we know how to build a barrier. But remember, I said before that a lot of the original electronics were rigid. So the question becomes, what happens? First of all, how do you measure it? How do you make sure that you don't have defects popping up? And then what happens when you start flexing these? So I'll talk about this a little bit as we go through. First thing that we tried was we used atomic layer deposition. So atomic layer deposition is a process that gives you very, very smooth films. It's very, very low defects. And so you can see here that we're alternating layers of aluminum oxide with hafnium oxide and making this nanolaminate architecture. You can see the scale bar here. So we deposited this on silicon because just for the carrier to do the TEM imaging. And so the first thing I'm going to show you is what happens when we put this on top of a calcium sensor. So that is the trick to measuring basically the diffusion of water vapor into the system. If I were to take a 100 nanometer thick layer of calcium, hold it up in the air, it would go from looking metallic to clear in about 10 to 15 seconds, right? And so now just keep that in mind, 10 to 15 seconds versus the time scales that I'm showing you. For instance, here is a barrier film on a calcium substrate, 192 hours, it's still sitting there. I've had a student have a sample that's been around for 3 or 4 years, and it's still sitting there. And so these are the kinds of things that you can utilize the calcium for. So the first thing we're going to do is let's take this silicon nitride layer out, and we're going to deposit the ALD layer right on top of the calcium sensor. And I said, okay, in case there are any particles on there, let's just go ahead and spin coat a layer of polymer. I'm thinking planarization like we typically do in semiconductor manufacturing. And here's what happens. So I have this SiTop layer. I have 200 nanometers. This is the initial. And what you see is you get the Swiss cheese effect. And what was interesting, I spin coat 4.3 microns of it on top. It actually looks worse. I'm thinking this polymer layer would cover up any particles. I put my ALD layer on top, and I should be fine. It's not going to come through. So why is it doing this? Well, first of all, we go back and look. Whenever we look at any one of these points right here, what you see is basically there's a particle, Okay, so that tells me in this process I have particles that were on my substrate, and you can actually see the crack. There's a crack there, there's a crack on here, and so that's allowing that water to come through, and you get this Swiss cheese effect. So it's basically diffusing in and eating the calcium as it spreads out from that particle. When we look at the thicker sample, what you see here are basically cracks that run all the way across. And so that again is eating the calcium much faster. So going back to sort of basic mechanics, what you could say is, all right, I have a thin film, I have atomic layer deposited film. It inherently has a tensile stress. I've put down my layer polymer, which I thought was going to passivate some of the particles. Obviously it didn't, but let's say if I don't have particles there whatsoever, what you find is that there's a crack driving force for any sort of defect that you may have in this ALD layer. It depends upon the stress. So if I have a tensile stress in this film, it's going to drive up the crack driving force, in addition to the fact that it depends on this parameter Z, and this parameter Z depends on this parameter alpha here, and it basically said that it looks at the sort of the difference between the elastic modulus of the film versus the substrate. So the higher the difference is, basically if I have an inorganic film on a polymer film, say a soft polymer film and inorganic film here, I have higher contrast, I'm basically driving up this driving force factor here. So it tells me that if I were to put this ALD layer directly on glass, it wouldn't have the same driving force as me putting the polymer here. The thicker the polymer layer, the less this ALD layer feels the effect of the glass substrate. So that's the problem. So basically what we figured out is that if we go in and we put a silicon nitride layer in and basically try to counteract the basically the stress in the ALD layer, or to basically give it a little bit more contrast in this particular factor, it would actually help. So now what you see here is that we put that silicon nitride layer in, and basically you see for any thickness of the polymer that we basically don't have that cracking anymore, except for the fact that we still have some around the defects. All right, so I won't run through this entire study, but the main thing is that we go in and we do some additional tuning of the parameters of the stress in the films. Again, we're talking about films that, let's see, I didn't mention these. All of these films are around 20 nanometers in thickness in terms of the ALD films. So we go through, and the silicon nitride layer is about 500 nanometers. And so we go through and we do this deposition and we start clearing things up. Then we start putting in these multi-layers. And what you see now, and again, as I told you before, 500 hours, you'll see what happens. And this is actually kind of a neat thing that you'll see. I'll play this video. What you see in this time lapse over 500 hours, you basically see the ingress of moisture from the edges. So now what we have is this layer that's sitting on top, but there's still moisture ingress from the edges. So the last thing that we have to do in terms of developing this packaging is that you have to worry about the edge ingress. And so therefore there's some additional engineering that you do to prevent the moisture from coming in. And so these are edge seals that you put on when you do the packaging. So a lot of times when you see this, there will be this adhesive, you bring this down, and then there will be some additional edge sealing, or what you do is you make the path length around the edge of the device very long, so it takes a long time for it to diffuse in. So this is the main thing that I want to point out. So we were able to go through and address the defect issue that comes just from the processing. So once you've done that, we've been successful at doing this and learning how to package. Now we finally get to the point of, well, what happens if I start bending these devices? So now what we're going to talk about is looking at how do these things fail. And so one of the things that we'll do is we'll take this sample, we'll put it on a polymer substrate, and we'll just pull it, and we'll look to see what happens. So the concept that we originally thought, and most people in the industry thought, is that if I take a look at the sample, I pull it, if I go to a certain strain, I don't see anything happen, it's fine. Pull it some more, nothing happens, it's fine. I pull it, and all of a sudden I see cracks. We say, okay, stay away from that strain level. As long as I'm below that, I should be fine. What you see here is this interesting curve. This curve right here shows you that depending on the thickness, that strain at which you pull it, you see the crack first form, that it actually goes up with decreasing thickness. So I want to make this thing thin, so I increase the strain at which the crack first forms. But the problem here is that the thinner I make it, then I may have some defects, and I may have now a pathway for moisture to come through. So there's a balancing act when we do this. So this is the classical curve that you'll see in terms of the reliability of these barrier films that are used in these electronics. And the thing that we questioned was whether or not this is the right curve. So here's an interesting set of data that one of my graduate students took. And we have these defects here. It's actually nice that they're in the view, so you'll see these two in the next picture. What you see here are these lines right here. It shows you that there are 6 cracks in this view. This is held at a strain of 0.95%. And then when I go and actually my student held it here for, this is 250 nanometer thick silicon nitride, hold it for 24 hours, all of a sudden what you see are 28 cracks in the same field of view. It says that there's subcritical crack growth. So if I were only to go and pull it to a certain strain, if I don't see anything, it doesn't mean that there's not time-dependent fracture in these films. So basically what we said is this concept, the onset crack strain, doesn't give the complete picture for reliability. So you have to do something else. So what we started doing was a number of experiments. We started mapping out the crack growth rate. So what I could say is that if I'm at a certain strain, the crack is growing slow enough, it may not propagate or may not propagate to a significant size over the lifetime of the device. And so that's sort of where we're going. And so what we're going to do is we're going to take these films, put them on these polymer substrates. We're going to go back and pull them, and we're actually going to go and look to see actually what happens to these cracks. So that's basically what these slides are saying. So the first thing we do is a microscope. You basically initiate a crack, you're watching it grow, you're actually measuring it, and you see a behavior that looks like this. So this is at 0.7% strain. You see the crack, the speed actually decreases. And if you start out with other strain levels, this is basically showing you from 0.7 all the way down to 0.5. These are the rates at which the crack will grow. Didn't really understand what's causing the crack to slow down, what's happening here. So we started doing a lot of analysis, and for one of these, we take a fib cut, and what you see here is at 0.6% strain. At a half an hour, you see this crack that has occurred in the silicon nitride, and lo and behold, another thing that we see after a long period of time, you see the crack is actually now propagating down through the substrate. So it says the substrate will also play a role in how the damage forms in these particular materials. Here's another piece of interesting data is that, let's say if we pull this at a very low strain level, we only see one crack in the field of view, so it's very, very sparse cracking. We see that it accelerates. And these, where you have multiple cracks, it decelerates. Okay, so it's sort of conflicting what's actually happening here. So what we're going to point out here is that the other thing is that when we do the fib cut here, you see there's a crack in the silicon nitride. Out here, you see the crack is actually going down into the substrate. So we had to turn to modeling and really figure this one out because it's hard to decouple all of these things from the experiments. So when you first start out, you have a crack that occurs in the silicon nitride, and this is the crack growth rate. It's growing really, really fast. If you have now additional cracks that form on the edge, what you'll see is that the crack growth rate will stop because now you're dissipating that energy over multiple defects. And now as you have cracking that goes down at the substrate, you will actually decrease that growth rate a little bit more, and then as the cracks begin to dissipate into the substrate, you see everything begins to drop. And so this basically tells us that G-force that is causing the cracks to drive, you can see that it follows this kind of behavior. So it's all about the way that the cracks are developing. And so there are a few other things that I'll point out in terms of what we've learned. So one of the things that we started doing here, and I won't show the data, is that we started playing around with other substrates that were tougher. And so therefore you could actually engineer materials such that you don't get this substrate cracking and you get a low density of cracking. And so therefore you can actually reduce the overall propensity for damage. Here's one that we thought was also very interesting that complicated things. So here we have this crack that we're testing in air. It does this classical curve that I was showing you. Well, when we test it in nitrogen, it's actually lower. So it says that there's an environmental effect here. And then what happens is if you take this device and you put it back in air, you see that it jumps up again. And now it comes back down to this curve. So there's this stress corrosion cracking behavior that occurs in the sample that they said that there are environmental interactions with this sample. So let's skip through that. So what we've been able to do is actually now go through and map out, depending on if you're in air, if you're in dry air, if you're in nitrogen, and look at different effects, including temperature, we're able to map out basically the crack growth rate versus the crack intensity factor. And so now we can create these regime maps that allow you to now go back in and look at the reliability of these particular films. That's in a manner that's much different than just saying the onset crack strain. The other thing that's quite interesting also is that being in air, humid air versus being in nitrogen, also the number density of cracks that you see also is affected. So basically we're creating these kind of reliability regime maps that we utilize in order to try to understand the reliability of these barrier films. So the one thing that I pointed out here is that that I mentioned before is that there's this environmental effect here. So the next thing we said is that, hey, some of these films are going to be used where they're touching the body. Some of them are going to be used in harsh environments. So let's start figuring out, how do these films corrode? And so we're using electrochemical impedance spectroscopy, where we have an electrode that's sitting on this glass substrate, and we coat it with our ALD films. We put them in various solutions, and we use EIS to basically measure things like changes in the impedance. So this film is started here, and the impedance is changing over a period of time. And you can see basically the phase and the impedance changing, which says that the film is corroding. And so we looked at phosphate buffer saline solution as our initial, say, biological solution. And you can see that the Al2O3 film basically fails. And now you can see basically the various rates of degradation. So TiO2 is actually a fairly good film, where I know that you can make it, it's biologically compatible, but it's actually fairly good for use in phosphate buffered saline solution. We also looked at saliva. Again, TiO2, zirconium oxide hold it quite well. And again, we can go back and attune the stresses in these films. And the last one, we looked at simulated sweat. So I will say, yes, there is a chemical that you can go to various chemical companies and you mix it with water, and it is simulated sweat. We are not collecting sweat to do this, or saliva. So nonetheless, here it is. It gives you this interesting effect. And so what you do see is that there are some more chemical reactions that happen in sweat. So this again goes back to this concept: if I am going to wear some of these electronics, then sweat can actually be a bad actor, even for these atomic layer deposited films. And what you actually do find out is that in some of these wearable shirts, that they only last for a few months between washing. The chemicals are exposed to in washing, and the sweat from your body, it actually begins to corrode some of the electrodes and some of the other connectors, and so therefore they begin to fail. And so we've tried to use some of these coatings in order to show that you can improve the lifetime, but overall you can see that still, even here, you form this zirconia chloride from the sweat right here in the beginning stages, so it has some degradation. But the thing that I want to point out here as we move forward is that there are all kinds of things that you can do with these coatings in order to help you put these electronics in harsh environments. Here's actually a flexible set of organic transistors, and a couple of colleagues had the fun of putting this in boiling water and show that it actually works up to 15 minutes. Why are they interested in this? They're wanting to understand the sterilization process to make sure that these flexible electronics can move through sterilization. Testing electronics in water. This is another one in salt water. LEDs here, and so it just shows you the viability of some of these coatings that you can utilize in order to improve the overall behavior of the electronics, or the lifetime of the electronics. But again, the mechanics is a problem in terms of the overall flexibility. There's still a lot to be done in terms of solving that particular problem for barrier films. Now I'll move to the other part of my research, which is the concept of looking at wide bandgap semiconductors. And so this is another area where packaging and understanding thermal becomes more important. What I'm showing you here is this electric vehicle. This is a concept car by Mercedes-Benz for their electric vehicle. Why did I pick this one and not Tesla? I was actually in Stuttgart a couple of weeks ago, and they let me ride around in this one in the city. Only thing they did is so you wouldn't notice it, they put a different shell over it. And they said, don't take pictures. But anyway, so it was kind of cool. So you get to ride around and see how this one works. But on my trip to Nagoya, Japan, the other one that I saw, which I thought was kind of interesting, the motivation, not so much making an electric vehicle, but it's the concept of providing the elderly transportation. What they've done is they've taken this wheelchair, they put LiDAR on it, they put other controls, and so you could take this wheelchair and you can actually automate it. It can actually find its way around a building and take a person from point A to point B. They've also put controls on it such that if I drive it myself, it doesn't allow me to run into the walls and things like that, or run into other people. So this concept here is, again, going back to the electrification of transportation. So all the way from a vehicle, which you typically see, this is kind of new, kind of in the lab. How do you do this to provide basically transportation for people that may have disabilities, or people that may be elderly? And then the other one that I thought was kind of interesting, this is another one that I saw when I was in Germany. This is actually a tower that's 240 meters tall. I actually did go to the edge. They took me towards the top, and I could look down this elevator shaft. So you look, and then you hold your cell phone, and you do this, and take the picture. You don't just stand there because it's kind of intimidating. But the thing that they're doing here is, how does this fit into the electrification of transportation? If you start looking at buildings, very, very tall buildings, you basically have to move up and down with elevators. The number of elevators in a building depends upon the ability to put the cables in, the space in the building that you could put various shafts. And so what they've come up with is this concept that I can actually take two shafts side by side, and I could put two elevators here. And what you see, this crossbar right here, this is a track that will actually turn, and it will realign itself with this track. So what this elevator here is doing is it was here, and it's translating over to this track, and it can move up. So once you have elevators that can go back and forth, you can make this pathway going up, this pathway coming down. Now I can put actually 8, 9, 10 elevators in between two shafts, and they can actually translate and move around each other. So where does this come back into the so this is a transportation issue. Where does it come back into electrification? Power electronics to drive these electrical drivetrains. There's no cables. It's all electric drive systems moving up and down the building. And so power electronics here, here, and here. And so there's various forms of transportation, and this is where basically mobility in the future is going, being electrified. When we start looking at these wide bandgap semiconductors, they're being used also in terms of power supplies for servers. They're used in RF, they're used in radar systems. Here's an interesting one where this is actually a laptop charger. It can charge 2 laptops, and you can see the size of it compared to a tube of chapstick. It looks a lot different than the brick that I have here for my Mac. And then variable speed motor drives and lighting. And so all of these cases, what you see are wide bandgap semiconductors that are actually going towards revolutionizing the way that we handle electrical power. So why is that important? If you simply look at the electrification and the power that's actually going into a lot of these devices, between 5 to 10% of the world's electricity is being wasted and dissipated heat in terms of power electronic circuitry. So, you know, for this guy, it may not be so much, but if you start looking at the addition of more and more electronics in various systems, and you start adding up that power that's being dissipated, it can add up to quite a bit in terms of the power generation that is actually needed in the world. And so what we're doing here is that by going to basically wide bandgap semiconductors, you're actually pushing the efficiency up. Even if you push the efficiency up by 1%, is actually, we start looking at the totality, that's actually a significant amount of energy that's lost based upon the propagation of those power electronic devices. The other thing is that you're looking at devices that are smaller. So now I'm taking the devices, making them smaller, I'm making them more efficient, but now your power densities are increasing when you start looking at these systems. So therefore the cooling becomes a big issue. Here's a map that's a figure of merit, called a unipolar figure of merit. And what is here to show you is that basically if I look at something called the specific on resistance versus breakdown voltage, basically I have a benefit by going to wider bandgap. So let me back up and show you what I mean by specific on resistance. What does this actually mean? So if I have a device, a power electronic device, it is supposed to block all the current when it's off, right? So it should have infinite resistance, and ideally when it's on, it should have 0 resistance and just let the power flow through, therefore I'd have no losses. Well, I don't have anything with infinite resistance, I can immediately switch to have 0 resistance. It just doesn't exist. So as it's switching from some finite resistance to another level of finite resistance, I get a spike in the power that's being produced, being dissipated in the device. And then so when it's on, there's an on-state resistance at its natural state of resistance. And as I shut it off, again, I get another spike. So this is where the heat loss is coming from. And so one of the easy things people will do, they want, again, this on-state resistance to be small. That's what this is, a specific on-state resistance. And so if you were to look at something like basically a breakdown voltage of 1,000 volts, what you see is that the specific on-state resistance theoretically is smaller for beta-gallium oxide than it is for GaN, than it is for silicon carbide, than it is for silicon. So it says that as I go to wider bandgap materials, I have this headroom that I can actually push this resistance down lower and lower. So again, going back to that loss. There are other things in terms of circuit design to try to deal with this part, but the natural resistance of the electronics basically tends to, the on-state resistance can go down. Again, this is theoretical, so we have to work towards these limits if I go to wider bandgap materials. And so for right now, the main ones that we're looking at are gallium nitride, algan, which isn't on here, and then gallium oxide. So these basically are in this range, and so these are the materials that are being investigated. So we actually have a Muri that's on this gallium oxide material. We're working with this gallium nitride, and we'll work with some of the algan and another Muri that we're involved with Patrick here. And so the parts that I want to show you here, where does this thermal issue come in, is that if I look at the way these things are packaged, I have a device, I have this power substrate, I've got a heat spreader and a cold plate here. This is sort of the traditional structure. There's of course some advancements that go into here. But if I look at the device itself, I also have some interesting layers. I have basically for the two-dimensional electron gas, I have algan on top of GaN, so I've got this interface, and I've got the gallium nitride sitting on silicon carbide, so I have another interface. So when I look at it in totality, I've got several interfaces that I have to worry about. The heat's being generated here, and so the heat has to cross this interface, has to cross that interface, which is this one, and all the way through. So the engineering of these interfaces becomes important in terms of the totality of the resistance that you see in these structures. And what we're doing in our program is we're dealing a lot with engineering the interface first inside of the device, and then we'll look at the interface here that's on the external edges of the device. So here we go. Here is actually an RF device. Some of these will look similar to some of the lateral power devices. And the first thing that you'll see is that if I want to do gallium nitride on top of silicon carbide, and again, I'll just show you, I had this cartoon here, I showed GaN on top of silicon carbide. They don't have the same lattice spacing, meaning that the materials, the lattices don't match up nicely. So in order to get very, very good material, I have to grow a material in between. So this shows gallium nitride, aluminum nitride on top of silicon carbide. All right, so you can imagine that this layer right here is going to give me some thermal resistance. This layer right here has a thermal conductivity, let's say on the order of, let's just say 400 watts per meter K. And if I have the heat that's coming here, it's coming down through here, one of the things that we could try is, let's increase the thermal conductivity of this layer. So if you want to increase the thermal conductivity of that layer, what's the material that you would probably go to? Let's forget about cost, just go shoot for the moon. And actually, I will mention that the devices I'm about to show you, they are being developed for space applications. Let's go to diamond. All right, so diamond, we're going to go straight to 1,500, 2,000 watts per meter K. We're going to blow silicon carbide out of the water. The problem that you have is, how do you grow these two materials together? All right, high thermal conductivity. I've got a heat management problem here. If I can get it into here, I can dissipate it. The problem is, same thing here. I didn't have the right lattice structure to do this, so I had to put an interface. Now I'm putting silicon nitride in here. The silicon nitride actually is not so conductive. I mean, it's not that great. And so what we found, and this is interesting, in the early days when we first started working on this, we were given some devices by a large company that said, hey, we've got these devices on diamond here. And we measured it, and this is actually back when Thomas Beecham was a grad student, and they were actually worse than these. And they're like, oh, can't be, you got to be wrong. So they claimed that, well, your student probably mixed up the devices. Yeah, this is back in the day, point to my students, back in the day when I would go in the lab. So I actually went in the lab and measured them, and came to within about 5% of what Thomas had measured. Like, you're wrong. What they didn't realize is that even though this has high thermal conductivity, this particular layer can basically negate the benefits that you would have of this layer. So you have to engineer that interface just right in order to realize the benefits of putting gallium nitride on a very, very highly conductivity material like diamond. So what are the issues that you have? So when I start looking at this material, you basically have, the way that you can grow this is that you seed the layer on top of this dielectric, and you have now nanocrystalline grains. These grains then grow up to become larger grains. And so you really don't get to the 1,500, 2,000 watts per meter K until you're way out here. This layer right here is where you get all of your resistance. And so I won't go into a lot on, because of the time, I won't go into a lot in terms of what's happening right there. But what I will say is that the thermal conductivity near the interface can be 10% of the bulk value. So it could be as low as silicon when you get there, or lower than silicon. So this is where you're getting part of your resistance from. The other part, as I said before, is this particular layer here. And so these are some results that were done by my graduate student Luke here in the audience. And so one of the things we said is that, well, if you think of it just from a mechanical engineering point of view, if this is your problem, then just make it thinner. right? So we all know this L over K, so if we just make it thinner, that resistance should go down. So what happens if we change it to a layer that's 5 nanometers in thickness versus what some people had been using, which was much thicker than that? And then we go from silicon nitride to aluminum nitride to an interface that doesn't have any silicon nitride there. So what you see, I just want you to focus on this area here. If you don't have any silicon nitride at the interface, you actually have the highest resistance. Kind of interesting. If you go to the aluminum nitride, we found that we had something that's about here. And if you go to silicon nitride, it is down here. So it's saying that, at least for this series of samples, that silicon nitride was performing the best. You have to go back to the ground truth of material science to tell us what's happening. So if I try to grow the diamond on top of the GaN without an interfacial layer, the hydrogen in the process starts etching the GaN. I get surface roughness. That surface roughness causes defects. Those defects scatter phonons, and so therefore it helps to drive my resistance higher. When you go to aluminum nitride, in this particular case, you have some issues with aluminum nitride. This is actually an older picture that I have. You have some deposition processes. There's also some debate over whether or not you have some interaction with the plasma process and the growth of the aluminum nitride. But nonetheless, what you see here in this particular case is either poor deposition of this aluminum nitride layer. You have, again, some roughness here. And the issue here is that you have this poor interface that causes thermal resistance. Now, when we get to silicon nitride, here's some interesting things. These are electron energy loss spectroscopy images. This shows you that you have the silicon nitride layer here. When you start investigating it, you see a little bit of silicon that occurs. So you get this conversion. You get some silicon nitride here. You get carbon that is occurring here. And you look inside, you get these silicon carbide nanocrystals. So what you thought in this original image was silicon nitride can actually convert to other materials. And you also see some roughness here. So it goes back to tell us that you have to try to control the conversion chemistry or whatever is happening here in these particular materials in order to make this better. So when we go through and we were working with another group, they were able to do a different process in terms of growing that layer. And again, going back to that 5 nanometer thick layer, and what I want to point out is the thermal boundary resistance here was between 20 to 25 meter square K per gigawatt for these series of samples that we looked at here. When you go to this one, what you don't see is that roughness. You see a very, very nice silicon nitride layer. And doing some of the analysis, what we found is only about 2 to 3 nanometers of that particular layer was etched during the process. It was much more uniform. And what you find is that the thermal resistance of this layer was on the order of, say, 9 to 10 meters square K per gigawatt. So you are actually able to drop it by doing the control of the growth of the diamond on this particular layer. So again, what we're now getting down to is a layer that allows us to really take advantage of the thermal properties of that particular diamond layer. And so again, a lot of this has to come through. What you'll see is that we're going to do a lot more of this in terms of not just measuring the thermal properties and the work that I'm doing with Patrick, but actually going back to this pure understanding of what's happening in the materials and why. Here's another set of data that I want to show you, which I thought was also kind of neat. This is done by Z, my other graduate student sitting in the audience here. What you see here are these ridges. So we said there had been some work that showed that if you pattern interfaces at the right length scale, you can actually get enhancement in the thermal conductivity and the thermal boundary resistance. So let's try this with diamond. And so what you see are these basically ridges here. We're going to basically change the period of these ridges, the spacing, from on the order of 800 nanometers down to 140. And we're also going to change the pillar height. And what we found is that if we had a flat surface, you see the thermal resistance here was about 22 meters square K per gigawatt, and it goes down to about 14 as you make these pillars smaller and closer together. All right, it's kind of interesting. So why does that occur? Again, going back and looking at what's happening in these materials, what you see is that between these ridges, you get the seeding of the diamond grows, you get this nice symmetry line here, the grains impinge on each other, and it forces the diamond to turn and grow in a preferred texture. So you get stronger textures as you put these closer together. What I mean by texture is that you're aligning the grains. So if you align these systems, then you get fewer grain boundaries along that pathway going down, and you also get higher thermal conductivity, you get larger contact area, and all of this helps in the overall lowering of the thermal resistance of these particular interfaces. Getting close to the end here. So the next one I wanted to move to quickly was beta-gallium oxide. So remember before I said you had GaN, going to gallium oxide is a little bit better. So this beta-gallium oxide is got all these things that are really, really nice. It's supposed to be cheap to grow. Again, I don't grow it, so I'm not necessarily vouching that it's cheap, but that's the concept here, that it's going to be cheaper to grow than bulk GaN. All these things that you can do with it. The main thing, just sort of zipping through the problem here, is that gallium nitride can have a thermal conductivity in the bulk form above 200 watts per meter K. It can be 220, 230. When you get to bulk beta-gallium oxide, 25. So now I have a device that I'm trying to push this power through, make it smaller, and I'm actually hurting myself with the thermal conductivity. So what do? Do you give up? So what we're looking at here is that we're looking at the aspect of how do you extract the heat through the contact. So can I design the system so I pull the heat out on both sides, which now says that the thermal contact resistance between the metal and the beta-gallium oxide will play a role. This was, for some of you in the audience, you may remember Brian Foley, who was here. He was a postdoc in our group. What he found is that in measuring this thermal boundary conductance, that it depended on the orientation of the beta-gallium oxide. And so that's something that we don't quite understand just yet. This is for aluminum on that particular material. And this is some work from John Malin's group at CMU, where he actually showed that when you change some of the metals, that you can actually get this thermal boundary conductance to actually go up to somewhere on the order of 450 meters squared K per gigawatt. So what we're trying to do in our work, and I'm sort of mentioning the future, we're trying to understand, is this interfacial chemistry, or is this simply the overlap of the phonon density of states between the metal and the beta-gallium oxide? So this is still an unresolved issue, and this is sort of where we're going in terms of how would you design the cooling and the contacts on the beta-gallium oxide. And not only do you have to do that, for if there are any electrical engineers in the audience, you understand that when I design this thermal contact, that I also have to have it as an electrical contact. So it needs to be an ohmic contact. It has to be that. If I need a Schottky contact, I have to do that as well, in addition to designing the thermal. So with that, I'm getting very, very close to the end here. What we've been doing is looking at, again, we're going to be looking at a series of devices where we have lateral, and again, as I mentioned, these lateral devices have these interfaces that we have to design here. We can actually take some of these materials and transfer print them to other surfaces that are high thermal conductivity. When you transfer print, you also, again, have to worry about how good of a contact do you have, what is the chemistry of that interface, how does that actually change the overall behavior. And then the final one is when we have these vertical devices, what you'll see is that I have to pull the heat out of the contacts. This is an interesting one with vertical P-in diode. Luke has been working on these as well. And one of my other students that recently graduated, he did, so P-doping in GaN is actually harder to do than N-doping. So you have a higher resistance material here. When you pulse it and you send a current through there, what you actually see is you do get the heating that occurs at the top. So it shows you that on the P side contact, that's where you want to pull the heat out of these devices primarily. So I'm at about 10 minutes to go. And so what I'm going to do is I'm going to go ahead and wrap up. If you have questions about any other aspects of the MURI, I will be happy to answer those. I do want to show one interesting set of data that we've been talking about since we've been here. And it's just simply, if you were to look at aluminum on sapphire, this is done by a collaboration between our group, other people in our MURI team, and Patrick. You can actually look at, if I deposit a metal on top of sapphire, that's just the best that you clean chemically, versus sticking it inside of a chamber, ultra high vacuum, you heat it to try to take all of the stuff off of it that's not supposed to be there. And what you'll find is that you can actually have, if you do like sputter deposition, other things like this, you don't get the thermal boundary conductance that you do when you have these ultra high clean surfaces, which are out here. And so again, going back to understanding this interfacial chemistry is very, very important in terms of how do you make these thermal contacts. So in conclusion, sort of jumping back to the beginning, flexible electronics, they're coming. You're going to see them in electronic devices that we carry, but you're also going to see them in devices that you wear. There is an issue in terms of the packaging. I didn't talk about thermal at all. When you talk about a lot of these flexible substrates, low thermal conductivity, grand challenges, how do I do power on flexible substrates? The other aspect is trying to understand the mechanical behavior. Much different than what you see with these laptops, with the typical electronic devices that you have. These are going to be long-standing issues that you have to begin to address in terms of the behavior of these flexible electronics. Thermal boundary physics will play an important role in terms of not only its understanding, but how do we design interfaces in these electronic devices as we move forward, especially as we move to wide bandgap and ultra wide bandgap materials. And then finally, the last one I'll mention is that I don't think you can solve any of these problems by just a thermal approach. It's got to take a multidisciplinary effort. You have to understand the thermal and the material science, and then finally the device physics at the end of the day in order to really address these. A long list. I could probably actually put a few more on this list in terms of people, in terms of the work that I've shown that we've interacted with. And I think that's one of the fun parts about my position is that I get to work with a lot of great people. And that's, I mean, it makes every day really, really good when I can do that. I've actually enjoyed my time up here, definitely talking tech and meeting a lot of people. And so with that, I'd like to end and thank you very much for your attention and answer any questions you may have.
Have you looked into depositing gallium nitride on something else other than silicon nitride or aluminum nitride? For instance, if you would deposit it on top of argon, or if you put a little bit of indium in argon, you create this almost seamless interface between argon and gallium nitride.
Yeah. So between argon and gallium nitride. So what's nice is that you can tune some aspects of the stress. So people will make interfacial superlattices in order to, like, if I'm going to deposit on silicon, gallium nitride on silicon, I use these argon superlattice structures. Typically when you alloy gallium nitride with aluminum, you drop the thermal conductivity. And so that's one of the issues you'll have there, even though you have a benefit in terms of stress. We haven't looked a lot at those particular interfaces. That's something that we actually even mentioned today in terms of what we might do there. But one of the tricks that you're going to start seeing people do in the future as it matures is growing the device, lifting it off of whatever substrate I just grew it onto, and then doing a plasma transfer bond to a non-native substrate. I don't have to worry about the growth. I just have to get it to stick and hold itself very well. And now I can transfer it to copper. I can transfer it, although the CT mismatch will cause a problem, I could transfer it to diamond or silicon carbide or whatever it may be. So that might be one way of getting rid of that aluminum nitride layer, gallium nitride directly on high thermal conductivity silicon carbide, and getting it to work.
In one of the slides you had the rough surface, and you said that the thermal resistance goes up.
Mm-hmm.
What was that assigned to? Was it assigned to roughness? Or was it
So we didn't do a calculation. So it would be, in my opinion, what's happening is that you have, number one, you have a surface roughness. The other aspect to that is as you're doing the growth, you're basically introducing defects into the gallium nitride layer because you're etching it. And so therefore, I think all of these things come into play in terms of what would cause the resistance to go up. So we don't have a model that says a certain amount comes from roughness and the rest of it comes from the defects that are introduced in that particular layer because of the etching.
Because you have some other data where you have some kind of roughness.
Bing. Yep. We have talked about that as well. There's probably a length scale over which you have this patterned roughness that actually causes things to increase, and there's another length scale at which it goes down. We don't understand where that crossover point occurs, and that'll be part of what we'll study in the future.
But I think your dirty interface might have inhomogeneities other than the shape of the interface.
Yep. I think you're right. That very well could be the case. So we'll look at a lot of ideal interfaces, and then we'll start adding stuff to it and trying to understand. Again, I get back to surface chemistry, roughness, those kinds of factors, things that we can control, and we want to see where do you get enhancement and where do things begin to go down. And that's the science that I think that we can try to bring in terms of understanding these interfaces. At what point should you control these things, and at what point does it not matter?
I'm just curious, when you go back to the ALD deposited barrier layers,
Yep.
This may be a very naive question, I don't know much about that work, but what was the motivation behind using half-cumulative laminates?
Bing. So two things. Stress. So by depositing multiple layers and doing the control, we're doing a plasma enhanced ALD, you can control the stress better. The other thing is that we're getting to the point that if I wanted to grow a 20 nanometer thick film, if I grow it with certain materials, like I showed you titanium oxide is great. Well, the growth time takes a long time, or hafnium oxide. Growth time is really, really long. And again, grad students don't necessarily come that cheap, or they don't necessarily want to do a 24-hour deposition in the clean room. So what you do is you say ALD, aluminum oxide grows quickly. I can use that, and if I mix it with hafnium oxide, it provides some of that chemical protection that I typically see with just the bare hafnium oxide. So I get stress control. I also get some chemical benefit by doing these nanolaminate architecture.
One more question? You talked about this orientation dependence in gallium oxide.
Yes.
So you think is it known if it's due to the orientation really, or is it just that the growth, depending on the orientation, the surface can get dirtier?
I don't think the surface is dirtier. I mean, it is an anisotropic material. I don't know if there's some other, again, I don't know what the aspects are that causes this, but in terms of doing the measurements, this is what Brian was finding through a number of these different measurements. And so it's not well understood at this point, but basically one of the things that we're taking from this is that people are trying to develop these beta-gallium oxide devices with different orientations. It was telling us that depending on the orientation you use, one may be good for an electrical aspect, but it's also going to give us some additional challenges, at least with aluminum, for that direction. Now, we may go through and find that there's a different contact that we put on that begins to negate that drop you see in the TBC. And so, so for what we did in our work was only aluminum, whereas what I was showing in Malin's work, they used different metals and showed that you can increase this.
Could you repeat what was the ratio when the maximum change in the?
Oh, it was a factor of 2?
Factor of 2.
Yeah. So it's real.
Okay. Oh, one more question. So when you're looking at the moisture and cracking, you were showing that it's nucleate new cracks as
Yep.
time. So how do those new cracks nucleate? Because it seems like that would be something that you would want to stop.
Exactly. So part of it, this could be part of it, that when we do the testing, because the fact in moisture they're growing faster, we're able to see them easier. The other thing that happens, which is interesting, is that when you look at the substrate we're using, it's called PET. Whenever it gets moisture into it, it plasticizes, so it gets soft. And so if you think about what I was saying before, that contrast between the elastic modulus of the film versus the substrate, you get a little bit of moisture in there, it softens the material underneath, and that crack can run much faster. So there's a stress corrosion cracking that occurs on the silicon nitride, plus the layer right underneath it that relieves some of the constraint to the crack opening, and that causes them to grow much faster. So
Of nucleating new cracks, because you're trying to dissipate the energy, and so it's doing that by nucleating
Yeah.
more cracks.
So what I guess maybe the thing to look at is that there are certain spots on there that are maybe very, very small defects, but because the moisture gets onto those spots, they grow faster. So again, the way that we're counting defects is simply by looking at them under the microscope. So there could have been a few of these that we didn't notice because they're so small with the optical microscope that they're actually there, but the ones in moisture grew large enough that we could see them. So there's probably this, in both cases, the same number of initiation sites. It's just that they had grown faster so that we could see them when they had moisture.